Okay, we're going to go through some practice questions. So question 28. A newly manufactured car is priced at $24,000. Each year, the car depreciates, that's a hint there, what might that refer to, by 25%. Write a recurrence relation to model this scenario. So I've got some questions off to the right here that I'd like you to think through. So first of all, is it arithmetic or geometric? And what tells you this? Again, how you approach a question, it might depend on whether it's multiple choice or short answer. And this one's a short answer one. You also need to work out, should I use recursion or the general rule? And here it said, write a recurrence relation. So we're going to use the recursive definition. And then another helpful thing to help you kind of step through a sequence type question is to always start with what you know. But here, we can see that a newly manufactured car is priced at $24,000. Each year the car depreciates by 25% and we're writing in a recurrence relation. So this is what they've written here. They said T0 equals 24,000, our starting value, and then we've got Tn plus 1 equals 0.75 Tn. So hopefully from that you've been able to figure out that this is actually a geometric sequence because the car's depreciating by 25% each year. So we need to use a common ratio to model that. If it was depreciating by a fixed value, if it was depreciating by 500 every year, then we'd know to use an arithmetic sequence because all we're doing is taking $500 off the value each year. And that's what we're doing again and again and again. But in this scenario, every year it's depreciating by 25%. So our R value, our common ratio is 0.75. And that's to illustrate that after every year, every time after 1 year has passed, the car is now worth 75% of what it used to be worth because it's dropped in value by 25%. And this is an interesting note here. I kind of alluded to this a bit earlier as well. Why am I saying T0 equals $24,000 when normally we start with T1? And that's because sometimes, this is where it gets quite tricky, sometimes in word equations, depending on what we've defined our variables as, sometimes we actually start with T0. And that's because in this scenario, we've defined n as after every year that's passed. So T1 is actually in this scenario after 1 year has passed. But here we're told the initial brand new value is $24,000. After 1 year, when we're looking at T1, it's already depreciated by 25%. So it wouldn't be accurate to say that T1 is $24,000 because a year hasn't passed yet if it's still worth $24,000. And now let's calculate how much the car will be worth after 4 years to illustrate that. So we've got our formula Tn plus 1 equals 0.75 times Tn. So what we're going to do first to illustrate that is we're going to say let n equal 0. So now we're going to have, if we say let n equal 0, we're going to have T0 plus 1 equals 0.75 times T0. And I know from up here that T0 is $24,000. And if I have T0 plus 1, I know that this is now T1. So by solving this out, I can now see that what we're saying is okay by substituting in n equals 0. Let me say that at the start. Let n equal 0, because that's what we've done here. By saying let n equal 0, we now know that T1, so term 1, so which is n equals 1, which is after 1 year has passed, our car is going to be worth 0.75, which is 25% less of what its previous value was. So our next, we have T1, like I've already said, equals 0.75 times T0. And because we know that T0 is the exact same as $24,000, because that's what equal means. Equal means like they're equal, they're balanced, they're the same. So T0, because we've seen T0, we can substitute that for $24,000. So what's 25% less of $24,000? Well, that's $18,000. So now we know that after 1 year of time has passed, our car has depreciated by 25%. Our car is depreciated by 25% after 1 year. We can now say that its new value is $18,000. Awesome. Now we're going to say let n equal 1. So by saying let n equal 1, now we have T2, term 2, is equal to 0.75 times T1. So now we have 0.75, not times 24,000 anymore, but actually times 18,000. Because after 2 years, it's going to be worth 25% less of what it was a year ago, not the original value, or it would just always stay at 18,000, which gives us 13,500. We apply the rule again, and now we've actually answered our question. So therefore, after 4 years, the car will be worth approximately $7,593.75. So that's our question there. Okay, awesome. Next question. The common difference for an arithmetic sequence is 16. Okay, so I already know we're talking about an arithmetic sequence, and I know we're talking about a common difference. And I know that it's positive 16. And I'm told that term 12 equals 236, but I'm not told the first term. So how do I find the first term? Well, I know I could work backwards using recursion. So I could put into my calculator 236 equals, and then subtract 16 and enter back until I calculated that I was back at term 1. But to do that a bit more mathematically and show my working, I'm going to use the general rule, which is the definition I have here. And I'm going to substitute in what I know, and then I'm going to work back to find out what T1 is. So I'm actually trying to solve in this question. What I want to find out is what is T1. So I'm going to define all my other variables. I'm going to say let n equal 12 because I know what term 12 is. I know it's 236. So that's actually another known value that I can substitute in to help me find n. So I'm going to say let Tn equals 236. I'm going to say let D, let the common difference be 16, because that's what we've been told. So now I can substitute in because Tn, we've said, is T12, so that's 236, is equal to T1 plus bracket 12 take 1 bracket 16. So now it's just a matter of solving and isolating T1. So I'm going to do 12 take 1 gives me 11. 11 by 16 gives me 176. And then to isolate T1, I subtract 176 from each side, which means that T1 is 60, which is awesome because I've already found term 1 now, which is really, really good. So that's how I would approach that question there. Okay, suppose that a savings account has $100 initially and receives simple interest at 5% per annum. How much would be in the account after 18 years? And then we can check our answer with our calculator. So we're not looking at financial maths yet. We're actually just looking at what are the applications of sequences to a simple interest scenario, which is lucky that I talked about a little bit about earlier about how I linked how arithmetic sequences can be used to model simple interest, because we're simply adding the same amount of interest every time. Whereas if we're looking at compound interest, that's a geometric sequence situation because we're multiplying by a common ratio each time, depending on whatever the annual rate of interest is. So I know that I'm looking for simple interest. But before I can start using my arithmetic sequence, I actually have to calculate how much interest they'd be receiving each year, which is kind of the only part of the question that's not like strictly sequence related. But because there's $100 in the account and the interest is 5%, all I've got to do is work out what 5% of $100 is. So by multiplying 100 by 0.05, I've got $5 more every year. So that's my common difference. That's how much is being added to the account every single year. So every single year, an extra $5 is being deposited into the account. So if Tn is the amount in the balance after n years, then T1 equals 105. Interesting, see what I've done here? I could have said T0 equals 100, and that's still equally as true, because again, now we're doing one of those practical application questions where our starting point before we actually do anything is what we want to have beforehand. So T0 after 0 applications of my rule is 100, because letting n equal 0, because here I've defined like Tn is the amount in the balance after n years. And because at T0, 0 years have passed, I know that there's $100 in the account initially, which means that T0 is 100. And then after 1 year has passed, there's $105 in the account. So I've defined that T1 as 105 so that I can use this rule here, because I can't use this rule with T0. I have to calculate T1. So that's what I've done there. And now what we're simply doing is substituting in our known values. I've now calculated T1. I know what D is, and I know that I want N to be 18 because I want to know how much is in the account after 18 years. So we substitute in. We're looking for term 18. So we do our math again. 18 take 1 is 17. 17 times 5 is 85. So now we have, in essence, we have 105 plus 85, which if we break down, it actually makes sense how our rule is working, because this is after 1 year. So this is our original amount plus 1 year of simple interest. And this here, 17 times 5, that's saying, well, okay, what if I added $5 an extra 17 times? So that's how I've got my 18 years worth of interest. My $100 is my principal amount. This $5 is how much after 1 year. And then this amount is how much after an extra 17 years. Which gives us our final amount of $190, which again, you can double check using calculator recursion. So I'd encourage you to try that on your calculator now to make sure you've got the hang of that. So therefore, after 18 years, there'd be $190 in the account. Awesome. So we don't have too much time left, so I'm not going to go through this question here. But again, it is in the slides, so feel free to have a look at it. This question is about how many bacteria would be in a petri dish after a set amount of time. And just to briefly go over the approach to the question. So what they've done is they've defined all the variables, they've calculated R, they've come up with a formula that they can use. And now that they've got this formula, the goal is to find N. That's the goal, to find N. But like what I said earlier, it's actually quite tricky to find out what N is because we don't cover logarithms in general maths. We actually can't kind of isolate N because that's just like kind of tricky in maths. So what we do to solve a question like this is we actually use trial and error and substitution, which is a completely valid mathematical approach as long as we're showing out our working. So what they've done here is they've literally found N by using trial and error. So they said, okay, what if we let N equal 20? Oh, no, that's too low. That's not what we're looking for. They did a bunch more maths. They said, well, what about if we let N equal 100? Well, that's too high. That's not what we're looking for. What about 50? What about this? So pretty much they just tried all these different substitutions until they got the number they were looking for. Oh, I actually believe it could potentially be a bit of an error in these slides. I don't think those are the right numbers, but lucky I'm just going over the brief overview of the question, the structure and the format. But yeah, that's the essence of how they did that. They used it during doing substitution. And then alternatively, you could have also used recursion. So that, for example, like doing it on your calculator of just taking the first bit, multiplying it by 1.15, and then multiplying it by the common ratio again, multiplying it by the common ratio again, until you got all the way to term 78. So when we're trying to solve for n in these kind of trickier questions, you kind of have the two options of trial and error or recursion using your calculator. And whichever one kind of works best for the scenario is totally up to you. Yeah, sorry we briefly kind of went through that question. We haven't gone through the exam answer exactly. And yeah, I believe there might be some errors in these slides here potentially. But I just wanted to briefly overview the approach to the question. That was my focus. Which